It's good to see you all. I'm with Paragraf. I'm going to talk a little bit about Paragraf as soon as the slides come up and what we're doing with graphene. It's been interesting. The first two talks have been about diamond and a form of carbon. We're going to move to a different form of carbon now and talk about graphene. So I don't usually like to start off with a corporate profile, but this is really more about the journey that sort of brought us to quantum compute and to this conference. Paragraf is essentially a foundry business. We're a new kind of semiconductor foundry business. The new is with respect to the kinds of materials that we bring to bear to the electronic components that we produce in our foundry. So we're focused on making use of 2D materials to really transform what's possible with different kinds of electronic components. The 2D material that we're focused on for our first foundry and the products that we produce in that foundry is graphene. So graphene, if you're not aware of it, it was discovered in the UK 2004, Nobel Prize awarded in 2010, and it's a form of carbon that is arranged in a two-dimensional hexagonal lattice. So it's one atom thick. Now, graphene has several very interesting attributes. It's superconductive, maybe not in the formal sense, but much more conductive than copper. It's optically transparent. It's biologically compatible, and you can bond different kinds of protein molecules, for example, to graphene. And as part of the foundry business, we're also generating products. So we're sort of an integrated device manufacturing model as well. For example, the first product that we've brought to market based on graphene-based electronic components is a magnetic sensor. It's basically a Hall effect sensor. So it's able to detect magnetic fields because of the kind of sensitivity and electron mobility that you find with graphene. We're also, for example, about to bring to market a graphene field effect transistor that is particularly suited to biosensing applications. So we're interested in that. And further along our roadmap, we're looking at the use of graphene in RF filters as well to help with 5G and the kind of energy consumption and power dissipation of RF filters. Now, when we brought out, and this is where we get to the journey, when we brought out the magnetic sensing Hall element, we began to explore different sorts of application spaces that it could help and particularly help with the application space. For example, we're finding great opportunity with the graphene-based Hall effect sensor in electric vehicles. There's a real pressure in the electric vehicle market to increase the efficiency, reduce cost, reduce size and power of the main parts of the powertrain and the drivetrain in those vehicles. So current sensing is really being scrutinized in high current applications. For example, the inverter and the kinds of battery management systems. So current sensing is a big application space, operating at thousands of amps in these high voltage, high current applications within the vehicle. But also within the electric vehicle battery manufacturing space, there's an opportunity for microamp sensing to detect bad battery cells at the end of line. So this is an example of the kind of dynamic range that you can achieve with graphene across widely different sort of magnetic fields and currents. But we also began to look at cryogenic applications. For example, in particle accelerators, where they're working with magnets at tens of Teslas, but in cryogenic kinds of temperatures, so working in very extreme environments. And then we encountered a use case within quantum compute. And this began to provide some clues as to maybe some ways that we could help in the quantum compute environment, which brings us to why we're here and trying to confirm some hypotheses that we have about how maybe we could help in the quantum compute environment. So we began to speak, especially in the superconducting quantum compute space, developers who saw the need for the ability to measure sub-microtesla at milli-Kelvin kinds of temperatures, so 10, 15 milli-Kelvin. So when you're really operating with the superconducting qubits or quantum compute environment, be able to really monitor on an ongoing basis the quality and operation of your shielding within the shielding around the qubits as well as outside the shielding, potentially being able to measure the environment around the amplifiers, be able to measure the magnetic environment at those levels, both at room temperature, before the quantum compute and the fridge are lower down to operational temperature. So the whole sort of range to be able to sample the environment across an entire kind of dynamic range of temperature, which you can also do with graphene. And also be able to do that in a very small sensing volume so that potentially you could have multiple of these kinds of sub-microtesla milli-Kelvin sensors positioned throughout the quantum compute DR to be able to sort of map what's going on in a kind of diagnostic ongoing management mode. So having multiple sample points and be able to measure in real time, not wait for a long time to get to the right kind of resolution, but fairly quickly in real time understand the measurements across these multiple sample points within the quantum compute environment. And that would enable all sorts of things based on what we were told and the early information that we got. Just more and finer mapping and resolution of the magnetic field environment. Also check on the integrity of the shielding. And we've already had some feedback from this morning about how the shielding can get damaged during normal sort of maintenance of the fridge and of the qubit environment. It can get cracked. And you want to be able to really monitor these things on an ongoing basis. For quite a while, I worked in the HPC, so in the classical compute space, installing AI training processors into data centers. And you start from attacking the benchmarks, right? Which we talk a lot about in quantum compute and with classical compute. How are you doing with performance and raw performance against specific kinds of algorithms? But as soon as you start getting into data centers, you know what they're worried about? Is management software, an ongoing monitor of that compute resource to know what it's doing over time if they need to transition to different sorts of compute platforms. So that ongoing monitoring and management of your compute hardware is really important. The challenges that we've sort of been hearing around existing magnetic sensing technology for that quantum compute milli-Kelvin kind of environment is around, space. It's got to be really small, and we're going to talk more about that. It's got to be really low power, of course, so it's microwatts, because you don't want to introduce heat into that environment. It's got to extend down to those kinds of milli-Kelvin temperatures, at least with superconducting quantum compute and with silicon spin bit. They're operating in those kinds of temperatures. Microtesla, so tens to 100ths of Tesla, tens to 100ths of nanotesla is what we're really talking about in terms of the use case requirements. And it really needs to be an end-to-end kind of solution where it's not just about the sensor and the performance, but how does it get wired into the actual measurement infrastructure of the DR? How is that data brought out, and how is it presented to the management software or to users? So that you need to sort of think that through as well. And there are extremely sensitive magnetometers that are used in these sorts of cryo temperatures, but they're focused on specific sort of nanotesla use cases, and really are meant to operate at cryo temperatures. They're also very long sort of long cycle to get to the kinds of resolutions that are required. So not specifically real time. And the requirement to operate from room temperature down to kind of milli-Kelvin is problematic as well. So you've got these pressures, small size, low power, high sensitivity, but also ease of use in terms of easy integration with the measurement infrastructure that's available. So we have done some proofs of concept. We work with the superconducting quantum compute provider that I just mentioned to do a proof of concept. And this was really the form and look and feel of the proof of concept sort of cobbled together just to get it into the DR, actually try it out during the operation of the quantum computer just to see how things went, to give us some feedback about where we were with the idea in a kind of collaborative fashion. So we were able to get a repeatable response down to 10 milli-Kelvin, which was the kind of target temperature domain. We've since are now moving towards a much smaller implementation of that. It's shown here in this picture in the bottom right at our booth. You can come and see it's actually smaller than that. So being able to have very small sensing volume to get more of a pinpoint accuracy of the kind of measurement points that you're interested in. We're moving towards lower and lower noise. Right now, we can get down to micro-Tesla. As we continue to move our magnetic noise roadmap further with the graphene-based sensor towards the latter half of this year, we expect to get down into tens to 100s of nanotesla. And because of the low power requirements of graphene, it's working in the kind of microwatt level that you're really targeting. So we're on the right track. The main reason for us being here and beginning to speak to the audience at this conference is to confirm that, yes, this is something that is actually of broader use, and we're on the right track in terms of actually productizing this, get feedback about where we are and where we need to be, the use case models, just basically gather requirements and feedback about the product concept. We have done a series of measurements on our graphene-based Hall sensor. We went to a facility in Birmingham, UK, to work with equipment that can run up to multiples of Tesla, because actually at that time we were very interested in how we could help with the kind of particle acceleration, high energy physics area. But while we were there, we also ran some trials to see, well, what if we brought it down into kind of milli-Kelvin areas, so 350 milli-Kelvin, and did like a 1 milli-Tesla sweep across it. And we learned a few things from that. It's not where we need to be for the kind of use case that we're talking about with in the quantum compute environment, but it gave us some good indications that, yeah, we definitely have line of sight of being able to fulfill that use case. It's a very linear response. It would be more linear than how it appears here. There was sort of interference from the very strong magnet control apparatus for this equipment. It's built for much larger magnetic fields than this, so we got a certain amount of noise and interference. But we got good linear response, good resolution at the milli-Kelvin, and we're quite confident that we can achieve the micro-Tesla that we're targeting and beyond. We're pretty confident of getting into the nanoteslas depending on the implementation of the electronics, and that's something that we'd have to work with a partner to really sort of comprehend and kind of design around. So we feel that we have the material properties, the electronic and the actual electronic component to meet the requirements, and already some good feedback about the form factor and implementation of the device. And we've also begun to, with that same provider, talk about the sort of end-to-end solution in terms of how it all needs to be wired up. I mean, we show a few of these kinds of 3-axis sensors. It's 3 axes, I didn't really explain that. It's 3 axes in order to isolate a specific volume in space to really sort of measure that volume in space for the magnetic fields. You can have multiple of these. This is diagrammatic and not to scale. They're actually quite a bit smaller than that. But we've had feedback that, yes, it'd be good to have, for example, one inside the shielding, one outside the shielding to get, you know, a picture of what's going on in both of those cases, around the amplifier, possibly in different layers of the stack to understand what's going on with the whole environment. And on an ongoing sort of compute infrastructure management paradigm that I can foresee in that kind of data center on the cloud, what I'm used to seeing is that real-time data rolling constantly. You're always managing the resource. You know exactly what's going on with every one of your compute resources. So you can easily move between compute resources depending on what the workload is and what the state of the compute hardware is. And this is all part of fault-tolerant, practical quantum compute. We think this probably fits with that, especially as it begins to scale up and move on to the cloud. This shows how, at least with this proof of concept, we brought the signals from the 3-axis probe based on our sensor through the existing output measurement infrastructure of the DR, of the fridge, out into our box, which we call the MIST. And that allowed us to display in through our GUI what the actual measurements were of the magnetic fields being sensed by our probe. Ultimately, how we think this would roll out, if this actually reaches fulfillment as a product, it would be that it would be integrated as sort of a standard feature in dilution refrigerators from the usual kinds of providers, so that it's just part of the measurement infrastructure, and perhaps there are options with respect to how many of these 3-axis probes you could have scattered through the fridge, but it would be just part of the ongoing information that's being fed back about the health and operation of the overall system. That's how we imagine, that's our hypothesis, but again, we're here to sort of talk to folks, and we're beginning to get some good feedback, but we're looking forward to being able to talk more over the course of the next day or so, and begin to develop right sort of conversations and engagements and collaborations to really begin to refine the product concept and its requirements. So just to sort of summarize, in investigating where we could go with graphene-based electronics, specifically the graphene-based magnetic Hall effect sensor, we got this kind of feedback, initial feedback from quantum compute providers about accuracy, the dynamic range, the sensing volume, and the implementation model within the fridge. We're just going into production with our sensor over the course of this year. We have a roadmap driving up our sensitivity and driving down our magnetic noise over the course of the year, towards the end of the year, especially for the automotive applications that we're going into. But it also plays very well into meeting the sort of sub-microtesla requirements for this space. So we're very open to talk more about product requirements and application requirements. So please feel free to come and see us at the booth where all the food is. So you're bound to see us there. Thanks.
We have time for a couple of questions. If there are any.
If you assume that there's probably about 300 dilution refrigerators a year manufactured, and you're going to add 4 of those, you're talking 1,200 a year. Are you going to do this as a service, or you're just going to do this through Oxford and Blue Force and Zero Point and Maybell?
Yeah, it would just go through those providers, and we would sell the 3-axis probes into those guys. It's not a huge volume business as compared to the volume of the automotive opportunities that we see, but it's a really interesting.
Or amplifiers like Novoselov is doing into China.
I'm sorry?
Or like Novoselov is doing into China for amplifiers with Highway.
Oh, okay. Yeah, I'm not aware of that. But yes, we would expect this to be something that would be sold through that kind of channel, and we're speaking to those kinds of folks about it right now. We just want to confirm the pull through, like the actual demand, and I think as this equipment gets more and more installed into the cloud, and with more conventional kinds of data centers expectations in terms of management infrastructure, I guess we'll see what happens.
Okay.
Thanks.
I have one question.
I think, what's the stability of these magnetometers? Do you have like Allen variances or?
Yeah, so in terms of drift, and for example, the kinds of sensitivity and performance drift over time, there are some very hard requirements for that in the automotive market. So we have to meet those requirements, which plays well into this market as well. Graphene itself as a material is extremely tough. It's the highest tensile strength available. So as a material, it's quite robust. And operationally, we have some very strict sort of lifetime drift requirements that we have to meet.
Okay, so you maintain the micro Tesla drift over, I don't know, a day, a year? Or? I mean, you're in the micro Tesla sensitivity?
Yeah, so being able to maintain sort of a consistency level of accuracy and sensitivity within the automotive market, you have to meet a drift requirement for 15 years.
Mhm. And so you maintain the same level.
Yes.
Okay, thank you.
Yeah, and within this use case, it's probably more forgiving because you know they're undergoing constant maintenance, so there's a chance to recalibrate and sort of make for corrections that might happen in terms of lifetime drift.
Thank you very much, Tom.
Thank you.